Hello, good morning everyone. Uh, in the previous lecture, we have discussed about the defined rules for block diagram reductions. Now, once you have learned the rules for block diagram reduction and you know what is the purpose of the block diagram reductions, next step is to solve certain kind of problem by which uh, you can be confident that any kind of block diagrams will be given to you and you can get the reduced form of it, right? So in this lecture we will discuss some of the examples and how to get the overall block diagram of the system. For example, example 1, we have considered a complex block diagrams, a system like this. Say R is your input, G5, G1, G2, G4, G3, G6. These are the defined systems and they are interconnected the the picture has been drawn, right? And this C is your ultimate output. Now what you have to find out, we have to find out the overall transfer function, that is C by R, right? So basic motto is to get C by R. That means in any case what you have to consider, first of all you have to consider whether the system can be reduced like this. This is the form actually we want to get. This is your G, this is your C, and this is your H. That means once any block diagrams given to you can be reduced like this, one will be input, one will be output, and one forward path gain and one backward path gain, then you can directly write this C by R is equal to G by 1 plus GH if this is negative feedback concentrations, right? So this is the way. That means first of all, any problem given to you, what you have to do, you have to look into the structure, that is there any loop or closed loop path formed in this structure, or is there any takeoff point or summing point available which can be shifted such that you can get the structure like this, right? Always the system structure should be like this. This is the first method, and so step by step we will go. What we have to do first, we have to just see whether this kind of blocks are available here or not. See, I can see this is a error block, this is one error block plus minus, and here you see this is a feedback path. That means the signal is coming here and that goes to the output side. From the output side via one feedback path it comes to the input side again, the error block. So this is the structure you have to know. So here how can it be done? First of all, I can see there is a takeoff point, and you see there is a takeoff point and summing point. So there is no rule how you can shift the takeoff point and summing point. That means interchange of the summing point and takeoff point is not possible. So what could have been done, that means first of all, if you can do it, we can do like for example, if you can shift say this takeoff point to this position. So what will happen if this takeoff point is shifted to this position? Say G1 and G2 will be in cascadely connected. There will be series. There is no branching in between them. So this will be one single block. So once this can be done, so first of all, other than this, there is nothing to do. So first of all, shift the takeoff point from this position to this point and redraw the structure. I am redrawing this structure like first step. What we are doing is that R, this is your G5, this is your plus minus block, this is your G1. So this takeoff point is now shifted towards this point. So what we have to do, we have to write here only G2, right? Once you write G2, then next part here the same path will be there. You will be having G3. This is in this direction and this goes to this point, right? I'm just removing this part. This problem is here. So what happens next? Here there will be another takeoff point. That means this takeoff point is shifted to this. That means when this takeoff point is shifted to the left hand side of the any block, left hand side of the block G2 to right hand side of that block, what happens? It has to be fast think, and rest of the things, yeah, you will get. This is your plus minus, this is your G6, and this is your output C. So what you have to do, you have to shift this point to these positions, right? And this, I'm just removing this part. Already I have drawn it, so this is of no use now. Now we have to shift this point from this to this, right? So this point will be shifted here, that means there, right? And now there will be certain manipulations on this block. The block gain was only G4. Now when you shift the takeoff point from the left hand side of any block to the right hand side of the block, what is the rule you see? We get the branch gain. That means the block of which the takeoff point is shifted to the right. So that will be just divided. That means here the original gain was G4. Now you are shifting this branch takeoff point to the right hand side of the block. So you have to divide this by the block of which the takeoff point is shifted from left to right. So that means this gain will be now G4 by G2, right? So takeoff point is shifted from this side to this side. That means this gain is used to get the manipulated gain. So G4 by G4 2 will be the gain of this block. And now you see these two are the takeoff points. This is the modified structure. Next part, if these two are the takeoff points, then this can be shifted, right? So I can shift like this. First of all, this is your G5, this is your G1, this is your G2, and this I take it as in this positions. So this is your G3. So these are some kind of tedious job actually. There are certain methods which have been already developed to find out the system gain accurately without so much tedious job, because once the system will be more complex, the job will be more tedious. And this is your G6 and this is your C, right? So what happens now? See this G1 and G2 are in cascade. So I can just write the cascade connections with the G1 and G2 and G3 and see this block. Now this block, I will just remove this original block, and in step 3 that I will have to do. Step 3, just make this cascade. That means this will be R, this will be G5, and next this will be error block. Next these two are in cascade connection. That means G1 and G2 are in series. So reduced block will be equal to G1 and G2, right? Next, as you see, this is your gain block having gain of G4 by G2. This is actually coming here. This is plus minus, and this is your G6 and this is your C output, right? And here you see there is a feedback part, gain G3, right? So now you can see what is happening there. In the fourth step, what we will do, in the fourth step you will just find out the normal loop like structure. So this is our desired. There is a loop, and here you see there is again a chance of reduction. So in a single step we will do the 2 steps output, that means 4. What we have to do, this is your R, you see, this is your G5, and what is this? This is the feedback path G3. Signal is going there, so here to there you get a closed loop feedback path, right? So what you have to do, you have to just reduce this block. That means first of all, in the numerator what will be this forward path gain. What is the forward path gain here? This is G1 and G2, and what is the feedback path gain? That is G3, right? So this is negative feedback, 1 plus G1, G2 and G3. This is the block. That means starting from summing block to all these blocks has been reduced like this. And next you see this stuff. What is this? This is kind of parallel operations, right? This is not the feedback path. So this signal is coming there, the same signal is goes there. So this signal goes there through this path, and this signal goes there through this path, and they will be summed up. They will be summed up because this is a summer block having one positive signal, one negative signal. These two signals will be summed up to get the overall result. And once this to this there is no block, that means the gain is 1. The gain is considered to be 1. If the gain is 1, so what is this? This is plus and this is minus. So 1 minus G4 by G2, right? So this is the reduced block, and then the G6 as it is, and this is C. Now see, this G5, G1, G2 by 1 plus G1, G2, G3, and this is 1 minus G4 by G2, and the final block is G6. So this all these 4 blocks are again in cascadely connected. So they are series connected. So last step, you see this is R, just multiply this term, right? So G5 into G1, G2, G6 by 1 plus G1, G2, G3 multiplied by G4 by G2, right? So last step, C by R, that means the output by input is this. So G1, G2, G5, G6 by 1 plus G1, G2, G3, 1 minus G4 by G2. So this is your desired result, and this is the reduced block from all these things. So what we have done, we have learned that if any takeoff point or summing point is to be shifted from either side on any block, so that is very important, such that a closed loop type of feedback loop is formed, either parallel loop or feedback loop. Once this parallel loop and feedback loop you get from the complex structure, so it will be very much easier for you to get the reduced blocks like this, right? So we will take another example. So this is our example number 2, but you can see this is kind of complex system given to you, and you see there are 2 summing points which are just taking place in the side by side. So first step, what you have to do, we have to concentrate on the system, and you see what we can do. We cannot just shift this block to this side because there is a summing point. We can shift this block to this side also. There is an option, and another option is that you can just shift this takeoff point to the right hand side of G3. So you have to understand which one will be better. You can just shift to this block to this there also, but as there is a takeoff point, I will prefer not to shift the positions of the takeoff point and summing point in such a way they will merge together. Better you shift this takeoff point to there, right? So once you shift this takeoff point to that positions, so what will be your structure? So structure I will write like this. This is G1, so this will remain same, plus minus, this is your S3 block, and this is your G2. Next, you see, this is the overall structure shown there, and here was the block. We want to get the block shifted to the right hand side of the G3, right? So this block will be this takeoff point. This takeoff point means this path, right? So this path will be shifted to these positions, and you see, if this path is shifted to this position, what happens from the left hand side to the right hand side? That means this path will be having gain 1 by G3. So here after this block you will get again 1 by G3, and remaining part will be remain same. Sorry, so this will be here, and this goes there, right? And G3, after G3 you will be having H3. This is your C. So you have, or we have shifted that, sorry, there is a path H2, so this will remain same, and this branch only takeoff point is shifted from there to there, and ultimately this branch will be having another gain, which is the gain reverse of the G3. That means you are shifting these positions from left hand side of the block G3. So gain G3 will be divided in this path. So 1 by G3 will be multiplied, and you get the structure like this. Or you can see, we can do it like this, as these two are, say these two are the takeoff points, and interchange of the takeoff points is possible. So I will write this part as like next step. This is your G1, this is plus plus, sorry, this is minus minus, this is H3, and these two blocks I will call it cascade connected, so that will be multiplied. I will simply write like G2 into G3, and this is your block, and this is shifted to this position, this is shifted to this position. So after that there will be a branch, again 1 by G3, then H2 block comes, that is negative feedback, and from here also you will be having negative feedback. From there you will get the output C, right? So till then what we have found is that, say this is kind of negative feedback system, right? This is a closed loop with negative feedback, isn't it? Because see, normally what you see, negative feedback path is like given like this, R plus minus, this is G, this is C, and this is H, right? So it may be on the from this top, so the structure may be like this. This is your G, and I can just write like this, R, this is your plus minus, so then also this is your H, so this is your G forward path. So ultimately what happens, the signal goes there to the output side, from output side via on feedback path, this is coming to the error block. So similarly here what happens, the signal, this is positive, this is input signal, and this is your forward path, and via this H3 block this is coming back. So this is a one you see this is known as negative feedback closed loop system. So this will be reduced in a single block. So in the next step we will third step. The third step we will rewrite the expression, and during examinations in the university curriculum you have to do all these steps, because until unless you do every steps, so there will be a problem, uh, because in that case you will be not able to get any marks maybe. So see, this is your R, this is your plus minus block, this is your G1, and this block, this is your plus minus again. Now where is this block will be reduced to a single block, where G2 G3 is the forward path gain and this is your feedback path gain. So what is this forward path gain? G2 G3 divided by 1 plus, this is a negative feedback, G2 G3 H3, right? So from here you will get path like 1 by G3. Okay, I will do it in a single step. Now see what you have to do. This is a branch, right? So once this is a branch and my G3, and this signal, the same signal goes there, right? So this path is divided into two sections. So we can write it like this. This is 1 by G3. This is H2, fine. Now as this is a single branch, so this branch is divided into two parts, so we can write from here another block of gain 1 by G3 and this part, right? So as the structure is like this, that means the signal is coming from here to there, and from there this is divided into two parts, so same signal is coming from here actually. So whatever be the signal going through this path, that same signal is going through this path H2. So that is why we can just separate this single line into two take-up points. Now from the structure shown in step 3, what we will get just directly the two sections. You see, this is one closed loop part where 1 by G3 into H2, this will be series connected, cascade connected, and that means this is your feedback path and this is your forward path, right? So we will write like in the fourth step, what we can write, this is you can write R, this is your plus minus, this is your G1, and this is your forward path gain. So G2 G3 by 1 plus G2 G3 H3 divided by 1 plus G2 G3 by 1 plus G2 G3 H3 into H2 by G3, right? This H2 into 1 by G3, they are series connected, and this whole is in the feedback path. So definitely this will be your single block, and you see this is your C, and here in the feedback path gain is 1 by G3. Now it is very clear to you that this is a single state closed loop path, closed loop feedback control system in generalized block diagram. This is your forward path. So forward path going to be equal to G1 G2 G3 by this. So G1 into this block will be multiplied, and we may call, as it is a very big term, so you may call it A. So in the next step I can write just the last step, step 5. What happens? You see step 5, that is R plus minus, this is your A into G1 forward path gain, this is your C, and this is your feedback path gain 1 by G3. Now you see this is your common block, known block, so you can write R A G1 by 1 plus A G1 by G3. So this is your C. So you can get C by R is equal to AG1 by 1 plus AG1 by 1 plus AG1 by G3, right? So this is the procedure how you can get the solution for any reduced block, like using the block diagram reduction technique. Either you can shift the take-up point, or you can shift the summing point, right? So that these are the two major thing you have to do during the reduction algebra when you apply this block diagram reduction algebra for practical problems. And we will try for the last problem here, and that will be sufficient to understand the block diagram reduction method and the algebra what we will call it. So look at the problem given in the board. You see what you can see is that there are sorry, it will be R1. So this will be two inputs. So when there will be two inputs, the rule is something different. What is that? In that case, you have to consider one input at a time. One input. I can write it one input at a time. One input at a time. That means when you will consider R1 input, in that case R2 will be taken as 0, and when we consider the R2 input, then R1 is to be taken as 0. So these are the rules. If there are three input in any system, there also